Sir, you are muted.
Yes, thank you, Bob. Thank you. Okay, now, okay. Okay. So now, just we'll quickly recall the definition of reflexive and some of the basic definitions. So a relation R on a set A is said to be reflexive if A comma A belongs to capital R for all belongs to capital A. Irreflexive relation is irreflexive if for every A belongs to A comma A is what? Is not in R. So A comma A is not in R for every A belongs to capital A. Symmetric relation is symmetric if A comma B in R implies what? B comma A is also in R. Antisymmetric. There are two definitions. I told that in the last class. The first one, this is from Venkatraman book. So the relation is antisymmetric if for two different elements, so A and B, and A comma B in R, then B comma A should not be in R. So then only we say that what it is what? Antisymmetric. So not antisymmetric means for two distinct elements A comma B, okay, A not equal to B, and A comma B in R, and also B comma A is also in R, implies what? It is what? Not antisymmetric. Okay. So transitive if A comma B in R and B comma C is in R, then A comma C belongs to what? Capital R. Okay. Now I think this definition is also useful to prove some of the theorems. A relation R on a set R on a set A is reflexive if delta is what? Delta is means identity relation. I think I told in last class. Delta is a identity relation. Identity. What is identity relation? Delta is equal to set of all A comma A such that A belongs to what? Capital A. So this is an identity relation. So a relation R is reflexive if and only if delta is a subset of R, and relation R is irreflexive if and only if R intersection delta is equal to empty. A relation R is symmetric if and only if R inverse is equal to R. A relation R is antisymmetric if and only if R intersection R inverse is a subset of delta. A relation R on a set A is transitive if and only if R composition R is a subset of capital R. Okay, next. I think here I gave the definition of what reflexive, and I gave some. I think these things are, and I finished in the last class. Okay, this is another definition of antisymmetric. A relation R on a set A is to be antisymmetric whenever A comma B and B comma A, both of them in R, then A equal to B. Then we say it is what? It is also antisymmetric. So that this is another equivalent definition. So if you have any doubt in the previous class lectures, you can ask to me. And then the relation R on a set is what? Equivalence relation if it is what? Reflexive, symmetric, transitive. A relation R on a set is said to be partial order relation if it is what? Reflexive, antisymmetric, and transitive. So, and then, yes, so I gave some examples of equivalence relation. The first example is what? Similarity, uh, similarity with respect to set of triangles. Okay. I think last class I told that similarity matrices in the lecture video, but it is not a similarity matrices. It is a similarity. Two triangles are similar. Okay, so here they are they mean similarity of two triangles. Similarity with respect to a set of triangles. T is an equivalence relation. So we know that every triangle is similar to itself. Okay, So that's why T1 is similar to what? T1. Okay, for every T1 belongs to what? Capital T. Capital T is what? Set of all triangles. Okay, and then T1 is similar to T2 implies what? T2 is also what? Similar to T1, and hence it satisfies symmetry. And the third one is transitive. So that one you can easily prove. Okay, T1 is similar to T2, T2 is similar to T3 implies T1 is similar to T3. So and hence it is equivalence relation. This is also class we discussed, and this problem I think I checked in the video. This problem I think I done it correctly. This one is also actually here a relation R on a set A is called the partial order relation. I think you know reflexive, antisymmetric, transitive. For here I gave one of the examples. So what is the example I gave? Here a set A together with what? Okay, what is the example? Yes, example is here the greater than or equal to relation is a partial ordering. So on what? On the set of all integers is it. So the reason is A is greater than equal to A for every integer A. This is true. Okay, that's why greater than equal to is what? Reflexive. Next, A greater than equal to A, that is A is related to B. This is actually what? A is R is what? Relation, this relation. And B is related to A. Here, what is the relation? Greater than or equal to. So implies A equal to B. So actually this idea, which idea just now I told, antisymmetric, yes. Okay, whenever A comma B and B comma A in R, then A equal to B. So then we say that what the relation is what? Antisymmetric. So using this definition, they are telling what? Here, antisymmetric. So next to transitive, A greater than equal to B and B greater than equal to C, you should assume from this you can easily prove A greater than equal to C, and hence greater than equal to is what? Transitive. So that's why set of all integers with respect to what? Greater than equal to is a partially ordered set, or you can say simply poset. Okay, and then I told that why it is poset. First letter P and then O and then set. That's why it is poset. Okay, now I think this is the last slide, and the last class we discussed, and then okay. Here in this note, I told that if A comma A is not in R for at least one A belongs to capital A, then the relation R is what? Not reflexive. Okay. Similarly, A comma A belongs to R for at least one A belongs to capital A, then R is not irreflexive. Okay. Now I think the last one, I think for not symmetric, if A comma B in R but B comma A is not in R for at least one pair A comma B, then and the relation is not symmetric. I think I explained this problem last class itself. You can refer it. This one is also I explained. The fourth one, okay. Here, this one is also I explained clearly, okay. Let n be the set of all natural numbers. Define a relation R on n as follows. So A is related to B if and only if what? A divides B. So A divides B means what? B equal to some K for some positive integer K. So then it is what? Reflexive, transitive, but it is not symmetric. Why it is not symmetric means the reason is why it is reflexive, because A divides A. So A divides A, that's why you can say what? A is related to A. That's why it is reflexive. Okay, transitive. How it is transitive? A is related to B. A related to B implies what? A divides B, and B is related to C. That is also you should assume. This implies what? B divides C. So A divides B and B divides C, then automatically what? A divides C. That's why R is what? Transitive. But it is not symmetric. Reason is 4 divides 8, but 8 does not divide what? 4. That's why it is not symmetric. But it is anti-symmetric. Why? How it is anti-symmetric? So whenever A comma B in R and B comma A in R, I should prove what? A equal to B. So A comma B in R, under this definition, A divides B. Okay, A divides B. So A divides B means B equal to what? Some n into A. And also we should assume what? B is related to A. Or B comma A belongs to R. That implies what? From this B related to A means B divides A. So B divides A means A equal to some MB for some integers, some M and N. So from this A equal to, I'll start from here. This A equal to MB. But we know that I'll keep M and B is what? NA. So A equal to MNA. Okay. So this is, here also you have A, here also A. So this is possible only if M and N are what? A positive integers. So this is A equal to M and A is possible only if M equal to N equal to 1. So M equal to N equal to 1 implies B equal to what? A. So M equal to 1 implies A equal to B or B equal to A. So that is I want to prove. So whenever A comma B in R and B comma A in R, I should prove what? A equal to B. So that is given here. Okay, then A comma B in R and B comma A is also in R. This implies what we proved? A equal to B. So this implies R is antisymmetric, and hence we proved R is reflexive, antisymmetric, and transitive, and hence the relation is what? Partial order relation. Okay. So now, so from here onwards, I'll start from today's topic. Okay, here you can see here this relation is what? Not reflexive. So because 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 is not here, that's why it is not reflexive. Not symmetric. Why it is not symmetric? 1 comma 2 is here, so 2 comma 1 is also is not here. Similarly, 2 comma 4 is here, 4 comma 2 is not here. So next one, so this relation is reflexive. Okay, 1 1 2 2 3 3 4 4 is here, so that's why it is reflexive, but it's not symmetric. 1 comma 3 is here, 3 comma 1 is not here. Similarly, 3 comma 2 is here, 2 comma 3 is also what? Not here. So any one, for at least for one element, okay, A comma B is there, but B comma A is not there, implies what? It is not symmetric, not transitive. Why it is not transitive? Check it. Yeah, 3 comma 3 and 3 comma 2 is here. So 3 comma 2, okay, it is here. Okay. 1 3, yes, 1 3 3 2 is here. So 1 2, please check it. 1 2 is not here. That's why it is not transitive. Look at this relation is symmetric. Okay, 1 3 3 1 3 4 4 3. That's why it's symmetric, but it is not reflexive. Because why? 1 1 is here. I don't have 2 2 3 3 4 4. Not transitive. Why it is not transitive? Yes, 3 4 and 4 3 is here, but 3 3 is not here. So that's why it is not transitive. So this relation is transitive. 1 1 1 3 means 1 3 is here. Okay, but it's not reflexive. You know that 2 2 3 3 4 4 is not here. It's not symmetric because 1 3 is here, 3 1 is not here. And this relation is reflexive. Okay, 1 1 2 2 3 3 4 4 here, but it is also symmetric. You can check it. 1 3 3 1 3 4 4 3 is here, but it's not transitive. So 1 3 3 4 means 1 3 3 4 means 1 4 should be here. So I don't have here 1 4. That's why it is not transitive. And then the relation is reflexive. 1 1 2 2 3 3 4 4. Okay, it is reflexive, but transitive. check பண்ணிக்கோ. Please check it whether it is transitive one. Okay, yeah, it is transitive. 1 1 1 3 is here means 1 3 is also here. Okay, that's why it is transitive, but it's not symmetric because 3 1 3 is here, 3 1 is not here. Okay. So the next idea is so A be a non-empty set and delta. Just now I told that in last class also told that delta is an additive relation. It's equal to set of all a comma a such that a belongs to capital A. Then delta is reflexive because delta contains the elements of the form what? Set of all a comma a such that a belongs to capital A. So that's why delta is what? Reflexive and symmetric. Symmetric, earlier I told that the relation R is symmetric if R equal to R inverse. Okay. So we know that delta inverse is what? Is same as what? Delta. Delta inverse means what? Just you should interchange the first element into second element into first element. Again, we'll get what? Delta only. So delta inverse is equal to delta. That's why it is what? Symmetric. And then transition. Transition, I told that transitive, not transition, transitive. So delta composition, delta is a subset of what? R. Because for transitive, I told that this condition, which condition? R composition R. R composition R is a subset of what? A subset may be equal. Okay. So here delta composition delta composition delta is equal to delta. So if it is equal to delta, it will satisfy what? Equality. Okay, this either subset, proper subset, or maybe equal. So that's why delta is what? Satisfies this condition. That's why delta is what? Transitive. So reflexive, symmetric, transitive, and hence the identity relation delta is an equivalence relation. Okay, next theorem. Let R and S be relations on S. Then I want to prove R is if R is reflexive, then R union S is reflexive. First, okay. First we will prove one by one. If R is reflexive, R union S is reflexive. R is reflexive means what? Delta is what? Subset of what? R. Okay. R is reflexive means if R is reflexive, delta is what? Subset of, maybe equal. Delta is a subset of R. If delta is a subset of R, delta is a subset of R union S. So if delta is a subset of R union S, then we can say R union S is what? Reflexive by the definition. By the definition. Next, second one. If R and S are reflexive, then its intersection is what? Reflexive. R is reflexive means delta is a subset of R, and S is reflexive means delta is a subset of what? S, and hence from these two, delta is a subset of what? R intersection S. So and hence if delta is a subset of something, that something should be what? Reflexive. Okay. So and hence delta is a subset of R intersection S. Thus R intersection S is what? Reflexive. And then third one, if R and S are symmetric, then its intersection and its union are symmetric. So we will do one by one. Okay. So assume that both R and S are what? Symmetric. So I'll take an element A comma B in its intersection. Okay, A comma B in intersection. Finally, I want to prove what? B comma A is in what? R intersection S. So this is we should know. You should assume this. You should prove this. Okay. So in intermediate step, we will do by logically. Okay, A comma B in R intersection S means A comma B is in R and A comma B is in what? S. So this is the first step. And then we know that R is symmetric. Okay, so A comma B in R implies B comma A is also in R. Similarly, But S is also symmetry. That's why A comma B in S implies what? B comma A is also in S. So now B comma A, its intersection. What is its intersection? R intersection S. So this implies whenever A comma B in R intersection S, B comma A is also in R intersection S. So R intersection S is what? Symmetric. Similarly, you can prove what? If R and S are symmetric, its union is also what? Symmetric. Next, transitive. Assume R and S are what? Transitive. Okay, we should prove its intersection is also transitive. So for this, I'll take two elements A comma B comma C in what? R intersection is. So we should prove what? A comma C in what? R intersection is. Okay, so A comma B comma C in R intersection S implies, so A comma B comma C belongs to R. Okay, first it is in R. So and hence R is transitive. So that's why A comma C in what? R. Similarly, A comma B comma C is also in what? S. So since we know that what S is also transitive, so A comma C in what? S. So A comma C in R, A comma C in S means A comma C, it's what? It's in the intersection. So this is the assumption. So thus A comma B comma C in R intersection S implies what? We have A comma C in R intersection S, and hence R intersection S is what? Transitive. So fifth one is if R and S are equivalence relation, then R intersection S is also what? Equivalence relation. Because we proved what already? Already we proved, okay, it is R and S are equivalence relation implies R intersection S is also what? Equivalence relation. So by 2, 3, 4, okay, 2, 3, 4 means what is 2? This is 2. If R and S are reflexive, R intersection S is what? Reflexive. If R and S are symmetric, R intersection S is also what? Symmetric. If R and S are transitive, then R intersection S is also what? Transitive. Using 2, 3, 4, we say that if R and S is also are equivalence relation, then R intersection S is also what? Equivalence relation. But we know that R and S are reflexive. Okay, R and S are reflexive. Okay, R union S is reflexive. Similarly, R and S are symmetric. R union S is symmetric, but R and S are transitive. R union S is need not be transitive. So that's why R union S, if R and S are equivalence relation, R union S need not be a equivalence relation. Here I am going to give an example. So maybe they will ask in 2 more questions. Okay. So if R and give an example of two relation is transitive, but its union is what? Or union of union of two transitive relation need not be transitive. Give an example. Okay, they will ask like this. For this, you should give like this. A is a given set 1, 2, 3, 4. R is this relation. You can check this is transitive, and S is another relation. This is also what? Transitive. So 1 comma 2, okay, in R. So 2 comma 3 in S. So 1 comma 2 comma 2 comma 3 in what? R union S. But 1 comma 3 is not in R, not in S, and hence 1 comma 3 is not in what? R union S. So and hence it is not R union of two relation is what? A transitive relation is need not be a transitive relation. So this is an example. Okay. So actually the next problem is So another way of proving R intersection, if R and S are symmetric, you can show what R, if R and S are symmetric, implies what R intersection is also symmetric. Already we proved. Here they are giving another proof. For this, they will use this idea. Okay, which idea? Actually, there is a exercise problem. 3. Okay, so in the exercise problem, they will first show that R union S whole inverse equal to what? R inverse union S inverse, and R intersection S whole inverse here inverse is missed. Inverse is equal to R inverse intersection S inverse. Suppose if S and R and S are symmetric, R is symmetric means what? R equal to R inverse. And S is symmetric means S is equal to what? S inverse. Or S inverse is equal to S. So hence R intersection S whole inverse. Here it is. But directly I am taking, this is I am not proving, but I will take, okay, first is equal to what? R inverse intersection S inverse. But R inverse is same as what? R. S inverse is same as what? S. So finally what we proved, R intersection S whole inverse is equal to R intersection S. So and hence R intersection S is what? Symmetry. So similarly, you can prove R union S is also what? Symmetric. So the next idea is, let R be a relation on a set capital A, then R is okay. So let R be a relation on a set capital A, then if R is reflexive, then R inverse is also reflexive. Okay, and if second one, if R is transitive, R inverse is also transitive. Third one, if R is equivalence relation, then R inverse is also equivalence relation. So we know that if R is reflexive, then delta, the identity relation is a subset of what? R. This implies delta inverse is a subset of R inverse. But we know that delta inverse is same as delta. That's why delta inverse is same as delta. And hence delta is a subset of what? R inverse. Suppose delta is a subset of something, already I told that something should be what? Is reflexive. So delta is a subset of R inverse here. So that's why R inverse is what? Reflexive. Second one, if R is transitive. R is transitive means, already we discussed, R composition R is what? It's a subset or maybe equal to what? R. This implies I'll take inverse on both sides. So R composition R inverse is a subset or equal to what? R inverse. But we know that we proved already R composition S whole inverse is equal to what? S inverse composition R inverse. So using this, you can write R composition R whole inverse equal to R inverse composition R inverse is a subset of what? R inverse. So what we proved now, okay, actually if R is transitive means what? R composition R is a subset of R. Similarly, R composition R is a subset of R. Now you can tell what? R is transitive. Similarly, now R inverse composition R inverse, the subset of R inverse. So this implies R inverse is what? Is transitive. So like this, okay, R inverse is transitive. But this one, instead of proving like this, you can prove the other way also here. Okay, how to prove the another method? If R is transitive, I want to prove R inverse is also transitive. So to prove R inverse is transitive, I'll take two ordered pairs A comma B and B comma C in belongs to or in R inverse. Okay, so A comma B in R inverse means B comma A and C comma B in where? In R. So and we know that R is what? Transitive. So C comma B and then B comma A in R. by transitive C comma A is also in what? R. If it is in R, okay, A comma C is in R inverse. So actually what I need to prove, A comma C should be in what? R inverse. So okay, A comma C in R inverse. That's why R inverse is what? Transitive. Third one, here you can see, if R is an equivalence relation, then R inverse is also what? Equivalence relation. Okay. So if R is an equivalence relation, it should be what? Symmetric. Symmetric means what? R equal to R inverse. Or you can say what? R inverse is same as what? R. But we know that by assumption, we know that R is what? Equivalence relation. R is an equivalence relation and R equal to what? R inverse. Both of them are same. And hence R inverse is also what? Equivalence relation. Okay, so next we are going to solve some of the problems in the equivalence relation. So here you can see let M be a given positive integer and N be the set of all natural, capital N be the set of all natural numbers. Let x comma y belongs to capital N. Okay, wait a minute. I have some call. I'll come in 2 minutes. Okay. So let M be the given positive integer and capital N be the set of all natural numbers. And let us take x comma y, two elements in the natural numbers. We say that x minus y is divisible by m if x minus y is equal to what? Some km for some integer k. This integer k may be a positive integer or negative integer. So that's why they are telling what it's a k is what need not be a positive integer. It may be positive integer or it is a negative integer. Okay. So if x minus y is divisible by m, then we can write what? X is congruent to okay y mod m. So we should read like this. X is congruent. This is congruent to y modulo. Okay, this is modulo. That's why mod we are telling short modulo m. Okay. Also, if x is congruent to y mod m, if and only if x and y leave the same remainder r when divided by what? M. So look at this example. Okay, 7 is congruent to 5 mod 2. If you divide 7 by 2, remainder is what? 1. If you divide 5 by 2, remainder is what? 1. So that's why 7 is congruent to 5 mod 2. So another way you can easily check it, how the difference, okay, 7 minus 5. 7 minus 5 is what? 2, which is divisible by, it should be divisible by what? Exactly divisible by 2. Okay, similarly 5 minus 2, that is also what? 5 minus 2 is what? Minus 2. Minus 2 is divisible by what? 2. Here it is a typo. 17 is congruent to 32 mod 15. Because 17, if you divide 17 by 15, remainder is what? 2. If you divide 32 by 15, the remainder is what? 2. Or instead of 32, you can take 62 also. If you divide 62 by 15, remainder is what? 2. And also 17 minus 32. Okay, 17 minus 32 is what? 15, which is divisible by what? Exactly 15. Even 17 minus 62. 17 minus 62 is what? 45. Okay, because 45 is exactly divisible by what? 50. Okay, now we'll go to the problem. So, okay, in this problem, prove that the relation congruence modulo m over the set of positive integers. So this is the relation. What is the relation? Congruence modulo m is the relation. Over what? Over set of positive integers is an equivalence relation. So first, they are defining what is n. N is what? Set of all positive integers, and m is a given positive integer. We define the congruence modulo m relation on this set n as follows. For x comma y in belongs to capital N, x is congruent to y mod m if and only if x minus its difference is divisible by m. Its difference is divisible by m. So what is the meaning of x minus y divisible by m? X minus y equal to some km. Okay, is equal to km for some integer k. This integer k is what? Either positive integer or negative integer. K belongs to capital M. Capital Z. K belongs to capital Z. Z is what? Set of all integers. Set of all integers. Okay, now I want to show that what? First, it is reflexive. So I'll take a x, y, z belongs to capital A. So reflexive means what I need to do. Okay, so x is related to x. Okay, I want to show what x is related to x. Okay, or instead of x is related to x, you can show what x is congruent to what? X is congruent to x model. I want to show that x is congruent to x model. So to prove x is congruent to x mod m, what I need to show x minus x is divisible by what? M. If I prove x minus x is divisible by m, then automatically what? X is congruent to x mod m. So x minus x is equal to what? We know that it is what? 0. But you can write 0 equal to what? 0 into m. This implies x minus x is equal to in the form of x minus x. Consider this is also x is equal to k. Instead of k, I have 0 into m. So this implies, okay, if compare these two. So when you can write like this, x minus y is divisible by m, you can write like this. If you write like this, you can tell x minus y is also what? Divisible by what? M. So that's why x minus x is equal to some 0 into m means x minus x is divisible by m. X minus x is divisible by m implies what? X is congruent to x mod m for all x belongs to capital M. And hence this relation is what? Reflexive. Okay. Next, x is related to y. Okay, x is related to y means what? Here x is congruent to y mod m. Okay, what do you mean by x is congruent to y mod m? X minus y is divisible by m. First you should write x minus y is divisible by m. So what is the meaning of x minus y is divisible by m? X minus y equal to k into m for some integer k. Okay, now instead of x minus y, if I write y minus x equal to what? Minus k into m. So what is the meaning of this? Y minus x is equal to some minus k into m implies, okay, so implies this is like this one, okay. These two are equal. Equivalent means I think look like the same thing. Here x minus y equal to km. Here what? Y minus x is equal to what? Minus k into m. So this implies we can say that y minus x is divisible by what? M. If y minus x is divisible by m, then we can say what? Using this, y is congruent to x mod m. So this relation is what? Symmetric. So next one, if x is congruent to y mod m and y is congruent to z mod m, okay, I need to prove what? X is congruent to z mod m. Okay. So if x is congruent to y mod m, x minus y is what? Divisible by m. X minus y is divisible by m. So x minus y is divisible by m means x minus y is equal to some km. Okay. Similarly, y is congruent to z mod m means y minus z is divisible by m. Y minus z is divisible by m means y minus z equal to some L. This is not 1, this is L. L into m. For some integer. For some integer, it may be positive or negative. Some integers k and what? L. Okay. Now I am adding the left hand side and also adding the right hand side. So x minus y plus y minus z equal to, if I add the right hand side, m is common, so k plus L into m. So y gets cancelled. So x minus z equal to what? K plus L into m. We know that k and L are integers, and hence k plus L is also what? Integer. So now x minus z equal to some integer into m. So this is like in this form. Okay, x minus y equal to some km. So instead of k, I have what? K plus L. So now this implies, what is the meaning of this? X minus y is divisible by what? M. The x minus z is divisible by m means x is congruent to z mod m. So since k plus 1 is also integer. So actually I want to prove x is what? Congruent to z mod m. So and hence this relation is what? Transitive. So it is reflexive, symmetric, transitive, and hence the relation congruence modulo m, okay, over what? Over the set of positive integers is an equivalence relation. So I'll stop here. So I have some other work now. Okay. Maybe we will discuss tomorrow. We'll solve more problem on the equivalence relation, and then we will go to next topic, transitive closure. First, we will finish equivalence relation tomorrow, and then if possible, we will go to transitive closure, Warshall algorithms in the next class. Okay, thank you.